All right, so each year the value of an investment increases by 0.49% of the previous value. So what kind of relationship is that? That's C, increasing exponential. So whatever our initial investment is, let's call it A, and let's call the function B. This would be 1.49. No, 0.49%, 0.0049 to the t for time. That's our function rule for that. Does that look linear? No, that's really not. We will get to this stuff after this current unit we're about to start. This is what we will do next. All right, planning a party, and this person pays $35 to rent the venue, and then $10.25 per attendee. So what is the greatest number of attendees? How do we do that? For $200. It essentially becomes this. Right? Take off the 35 you have to pay right up front, and then divide by $10.25. And then what is that?
16 guests.
Okay.
So they have 0.01 guests.
We could. And we should do this, right? Actually, let me write it. Let me write that as a separate statement. In other words, we don't have to invite 16. It says what is the greatest number, but we don't have to go that high if we don't want to. Maybe we only like 10 people and don't care if we have the other 6. That would be me.
Oh, okay.
It would struggle to be 10.
Like my father.
Number 18, the population of Greenville increased by 7%. If the 2016 population is K times the 2015 population, what is the value of K? In other words, what are we multiplying the 2015 population by to get the next one? That one, okay? And again, it goes back to the same idea. It's really, I want you to think about P being population. So times 1, that gives you the previous year's population. So P times 1, that's the population from the previous year, plus 0.07 is that 7% growth on that population from the year before. So those two are exponential models, and really, really useful. That stuff comes up a lot actually in finance and other like population growth, microbiology, that kind of stuff. It's really important to learn. This is an absolute value equation. Do you remember how to do that? Okay, so we're going to set 4x minus 4 equal to the positive version and the negative version.
Oh, math.
Huh? It says, what is the positive value? What does that mean?
To focus on the positive side of it.
Well, it depends, actually. It wants this to be positive. So it may be the positive result or the negative that makes it that way. Just read the question carefully. Anyway, if we solve these, so we'll get 4x equals 116. And what is that? 229? Yeah. That one will not be positive. So in this case, we're using the positive, and x minus 1 will be 28. But it could be worded in such a way, like if this was negative x minus 1, then the positive version, you'd have to solve the negative absolute value. See the difference? So it just depends how the stem of the problem is worded. So read carefully. How'd those go? Out of 4, how many did you get? Legit, not just guess. Okay. All right. Well, let's title your in your note packet and talk about this next unit. So this is called rational functions. What is the root word of rational? Didn't you guys tell me it was rat?
Okay, well that seems like it would be it.
So this is a unit about rats. Of a math of rats. Rats are so disgusting.
I think that'd be great. We could all do like a rat. No, they're actually super clean. They keep them from
They're disgusting. My wife worked with a lady that had rats as pets, and she would like let them crawl up through.
Oh no, that's too much.
Like,
Keep them in a cage. No,
yeah. So what is actually, in this case, the root of that word?
Rat ratio.
Okay. Ratios look like fractions. So this unit is about algebraic fractions is what we'll call them. And rational functions are basically taking what we did last unit, two polynomials, and putting one above the other. Okay?
Yeah.
And then a big focus of this unit is graphing, which not everybody really loves, but that will be, it's at least half of the focus of the unit. Can you graph a rational function? To do that, you'll be finding key features like we have, only this is a little bit more involved. And then the second half of the unit is all about operations with these. So multiplying and dividing are the two easy ones. Adding and subtracting are the hard ones. In fact, that will be the pinnacle of the unit. And then we'll end with solving rational equations. So as long as you can do two things really well, which are factoring, you will factor and factor and factor in this unit. And then any kind of fraction operations, if you're okay with those, this will be fine. It's not a big deal. Okay? And I feel like we've done a fair bit of review on those things, so it shouldn't be a big deal. The first section feels disjoint from the rest of the unit, so I'd like to kind of work through it quickly today and perhaps even finish and move through it today. But it does lay a foundation for what we'll see in the graphs for this unit. So I just don't like this first section because it feels weird. So this section is called inverse variation and the reciprocal function. What does the word reciprocal mean? It doesn't mean opposite. Yeah. So we're just switching positions of denominator and numerator when we say reciprocal. Which does include whole numbers as well. Like what's the reciprocal of 5? 1/5. 1/5, good. Okay. And then this word, inverse variation, you might have talked about in Algebra 1 maybe. It stands in contrast to direct variation. So what do you think direct variation means? Tom, can you put that away now? What is direct variation? I'll give you an example of an equation that's direct variation. Like the most basic one.
Like one directly affects the other.
Okay.
So like if you change y, like there will be the exact same.
Okay. So that would count. This is also. This is also. Those are all direct variation. What kind of relationships are all three of those? What would we have called them 5 minutes ago? Linear, right? Okay. So positive slope versus negative slope, does that make a difference?
Yeah.
Yes.
Okay. Here's inverse variation. So we'll talk about how these look toward each other. So those are examples of inverse variation functions. What's the difference?
X.
X is a negative.
That's a big difference, right? I mean, it doesn't look too different, like in terms of this has 3 pieces, that has 3 pieces, but these two are entirely different in their graph, in their meaning, and their behavior. So I asked you this, and you said it does make a difference. Let me know what you mean by that. Is this still direct variation?
Yeah.
Okay. So I put a negative slope. Tell me about that.
It still affects the line.
Okay. So yeah, big idea. So this is going to be kind of what our parent looks like a little bit. But the big idea is with x in the denominator, we introduce a bunch of restrictions. Not a bunch. We introduce a gigantic restriction on how these can operate. What would that be? Can you think of that right now? If I give you y equals 2 over x, there's an enormous glaring restriction on what x can be.
Oh, it has to be a multiple. It has to be
So I want you thinking about what would cause that. Let's just focus on this one. What would cause that to fail, to not be defined, to not work, those kind of things? If what was 0? Why? Can you divide by 0? Okay. So right now, I need you to lock into your brain for the entire unit. I want you to lock in that we can't divide by 0, and therefore a large part of what we do in this unit is going to be avoiding that and addressing where that happens. Because things go crazy and they don't work out when we divide by 0, right? Okay? So let's see if you can predict what this graph would look like. And we'll just focus on the first quadrant. If I say 2, and what we're going to do is, you remember the idea of limits from last unit? We just,
Yeah.
that was yesterday. Okay.
Really, he takes his test and does it when you're out the other.
I hope not. Okay, so we did this, limit as x approaches. Remember that?
Yeah.
On the last unit, we were talking about end behavior as x went to infinity or negative infinity. I want you to think backwards now. The limit as x approaches 0 from the right. So with that plus sign, we're saying get closer and closer to the x, or to the y-axis from the right. Can everybody visualize what we're doing?
Yes.
Okay.
Yeah.
All right. So I'm going to plot just kind of a basic graph. Just that quadrant, the first quadrant. And we'll just do successively smaller values and bigger. Actually, we'll do both. But let's start with the smaller one. So 2 over 1 obviously is what?
2.
Okay. So y equals, put that a little closer. Y equals 2 there. Okay, and then let's just get a little bit smaller. What if we do 2 over 0.5? Can you do that? Or 2 over 1/2, either way. Nope, apparently not. That's 4. You did?
That's what I said.
Good job, guys.
Oh, yeah.
Okay, remember we're getting closer and closer to the y-axis, so that's going to be a little bit closer. Okay, what if we do y equals 2 over 0.01, or 0.1, excuse me.
1.
Huh?
I said I'm scared they answer.
It's 20. Okay, so
20.
we're getting closer, but we're still a long ways. If you think infinite, we're still a long ways from the y-axis, aren't we?
Yeah.
Okay, so at 0.1, we're way up here at 20. Okay, what if I did y equals 2 over 0.0001? Now where are we?
Hundreds, thousands. 2 move.
20,000.
Yeah, sorry.
Okay, and it's not like 0.0001, and that's small. That's a small decimal, but it's still measurable even without. Yeah, you might need a microscope to see something of that measurement depending on the unit, but you would if it was like meters. But anyway, it's not like it's teeny tiny, right? It's not atomic scale at all, and we're already up to 20,000. Clear up here. Okay, let's go the other way. So actually, before we do, the limit as x gets closer and closer to 0 from the right is what? What are the y values doing as we skinny up next to the y? They're shooting up to infinity, aren't they? So this thing is ramping up here, heading to infinity.
Oh, is this one where it goes like this?
Yeah. Okay, let's go the other direction. What if we do y is 2 over 100? So now we're going to analyze the limit. Limit as x, that looks like lima.
I wasn't the same.
0.0. Okay, so as we go take off out to the right like we've seen. 2 over 100, what is that?
Oh, don't even listen to me.
Okay, so that is, and 100 is way out here, but that's 0.02. Okay, let's do, I'll put one in between here. What's 2 over 10? 0.2, okay? So somewhere, obviously, here in the middle. 0.2. Okay, and then if we go out farther, 2 over 10,000, that would be the analog of this one. Okay, so what's happening as we get way out there? What is it getting closer and closer to? The y value, so the limit as x goes out to the right, as x goes to infinity, of f, it's getting towards what?
0.
Towards 0. Good. Okay, so first of all, we notice two different limits. As we're going closer and closer to 0, it's shooting up to infinity. As we go out to the right, it's getting closer to 0. So as Tom pointed out a second ago, I'll do it this way, see better. Here's the shape of our graph. On the first quadrant, at least.
And it will be opposite.
It will never touch 0. Because, as if you think about continually making the denominator smaller, then the numerator, the whole thing gets bigger and bigger. But I can't ever get to 0. Why? No.
Because you just keep getting smaller and smaller. It's not.
As soon as it gets to 0, the whole thing falls apart, right? It's like building a tower with cards, and you're just building and building, and it's getting cooler and cooler, and then you put that one last card and the whole thing crashes. That's this. If I put 0 there, the whole thing falls apart and it's undefined. And that's why there will never be a graph on the y-axis, because we cannot divide by 0. Where do you, there are two parts to this graph. There are two wings, if you want to call it that. Where do you think the other wing will be? And it looks similar, but it's... Yeah. So if we get closer and closer to the y-axis, closer and closer to 0, but these are all negative, so -1, -0.5, etc., that's going to make really big negative numbers. You see that? Yeah. So all of what we wrote on the first quadrant will be mirrored on the third quadrant. And then similarly, if I divide by -10,000, it's very close to 0, but from the bottom. Okay? So that's the big idea of what these graphs will look like in various ways. We will have a lot of variation in that base model, but they will all have some version of approaching a line that it can't ever touch. And why is that again?
Because it'll just shatter it and
You can't divide by 0. Okay? So that line you're approaching is a divide by 0 no-no.
Is there a way to say, take the one in the top right? Is there a way to shift it 1 unit to the left?
Yep.
Touch the y-axis, but then it wouldn't touch negative.
You got it. So guys, this is what he was just bringing up. What if we wanted to move this thing around, this rational function graph? Would it be possible to graph it like this, maybe? No, let me do better. And have a vertical line that it approaches there instead.
Well, it should be possible.
How have we shifted things, in this case, to the left? How have we done that in the past? H was to the left was plus 1, right?
Yeah.
Or
To the
plus
right.
whatever.
To the right is
To the right was minus. Okay, what if we wanted to shift this whole thing up or down?
say
Plus,
you multiply a above.
Plus k, the k at the end, right? That
Yeah.
shifted it.
Plus or that.
Okay, and then he's talking about multiplying, let's say, by 5, or multiplying by a fourth. So what we see happening with these kinds when you multiply, do you remember the letter that we use for that? A. What we'll see happening, like if we multiplied by 5, is it draws it away from, like, I know this is getting busy, I'm sorry, but you can't even see that at all. This point right here, let me just put a circle there, is our new origin, and it draws the curves outward away from that, or puts it closer. Okay? That's kind of the changes these things will make. But
Are you gonna, probably not here, but are we gonna see ones where instead of going like this, it's like flipped?
no, not for this. Here's some variations of the graphs that we will have once we get more into the rational functions. So we might have some that do this. We might have some that do the bottom version of that. A lot of ours will have 2 lines that they can't touch. So maybe something like this, like that, and like that.
That's scary.
no.
Okay? So way different than graphs we've seen. These have multi-parts. A lot of them have 3 like that. They have lines both vertically and horizontally that they can't touch because they're dividing by 0. Yeah, we haven't seen anything like this, but these are cool graphs. They're a little bit sometimes hard to graph. Here's another version. Maybe we have one of these vertical lines, but we also have a diagonal line, and then our graph tucks in here and here, like that. And we'll have to find all those different ways that these look, because you can't just look at the function and know. You know how in last unit, if it was x to the 6th, you knew it both pointed up, right? And then you could find multiplicity and all the stuff to find the details. So we'll have to find the details, just like we did, in a different way, but we'll find details for all these. They're cool. They're pretty neat graphs. If you look on that poster, it's the right middle parent function. It's hard to see if you're over here, but that's kind of like the base model version of it. Okay? So factoring, fraction stuff, and then graphing. Let's get into like I said, the base model. This is called the reciprocal function. We'll come back to that maybe. Yeah, let's just get on here and do it there. So I want you to get kind of all this stuff we've been talking through forms the foundation of the unit, but the details of how become a lot more clear after this first section. So let's talk about inverse variation. First. Here's the basic idea. I think we'll just say it really basically first. So x and y are changing in opposite directions, opposite ways. Maybe I'll slash ways. So if x is getting bigger, y is getting smaller. And smaller doesn't mean more negative. It means smaller sign-wise. Okay? I said that weird. Size-wise, not sign-wise. Okay? So this is way more, it's deeper than this, but as x grows, y shrinks, and vice versa. Okay, again, can everybody pause before you write that? Just, I want you to clarify something. I'll give you time to write it. As x grows, y shrinks. I don't want you to think of it like just a downhill linear function. Because you could say, well, x is getting bigger and y is getting smaller, but it's getting more towards the negative, right? It's not getting a smaller. I mean, technically, if this is 10, and then obviously, like right there is y is 1, so the size got smaller, but it keeps going down in a way that says, oh, now I'm negative, -5, -10. Now I'm getting bigger, but negative, right? It's different than the one we saw a second ago that does this, where it just keeps getting smaller, not more negative. See the difference? Okay. It's important, but kind of subtle. Anyway, go ahead and write that. What this creates is a circumstance, and you saw me write this a bit ago, where we can write x times y equals k. And if we solve for either x or y, maybe I'll put it over here. Y equals k over x equals k over y. But anytime you have variables, one in the numerator, one in the denominator, they are inversely related. Inversely related. So k is called a constant of proportionality. That phrase constant of proportionality is not just a math thing. You physics guys, have you studied springs?
Yeah.
So like the spring constant is a constant of proportionality, right?
Yeah.
So the force is proportional to the amount of spring compression or stretch, either way, based on some spring constant K. You remember that?
Yeah. I feel like
Oh well, it's usually like F for force, spring force equals kx, where x is the distance of either, like some springs you get all springs you get a force by compressing or stretching.
Yeah, so
It wants to return.
Yeah, if you want to find the k variable in this one, you would divide by f.
Yeah.
And
If you could measure, like pull and measure some force and displacement, then you can find the spring constant. Yeah. Good. Alright, guys, so inverse variation, we're going to mention it, and then you won't really hear it the rest of the unit. So I don't want to belabor this too much. Let me show you some of the problems that these have. Here's a good example. Both of these rectangles have the same area. So, and they're poorly drawn examples in here, but but basically the idea is this. If I increase the length, what does the width have to do? Decrease. So we have this skinny little width of 2 inches times 72 length versus 6 and 24. They're closer together, but still equal 144. So as one went up, the other had to go down to accommodate that, right? Okay? Can you think of an inverse relationship in everyday life? As one thing goes up, the other thing goes down. In a proportional way, roughly.
Like how long you're awake compared to sleep.
Okay. So he said, if you didn't hear him, like how long you're awake versus asleep. If you sleep more, you're awake less and vice versa. Okay? Yeah, good job. What else?
When you read a book, like the larger the number of pages you've read, the lower you know.
Nice. Yeah. I'm not a big reader, but when I read, I'm talking like maybe a book a year kind of reader.
What?
And so when I read, I always look when I'm done for the session. I always look how much like the thickness of the pages I've read, because that's just a thing for me.
One book a year?
That's
Yeah.
crazy.
I read a lot of stuff. I just want to read more books, but it's not. My wife reads like all the time. All the time. It's cool, and I wish I could do that.
I
But,
like
You can find a book that you like.
books that I'm actually
Yeah.
interested in.
go ahead. Ryan.
The more you keep driving, the more gas needs to be.
Yeah, so as miles increase on your car, your gas volume of gas in your tank decreases. Awesome. Did you have one?
Yeah.
Okay.
What about like
One of the few
Supply and demand are inverse. As supply goes up, I guess demand could remain constant, but sometimes goes down. But yeah, as supply goes down, like were you involved in the whole toilet paper thing at all?
Oh my gosh, yeah.
Yes.
Like that was a good example. Yeah.
From all the stores. We only had one, but from all the stores.
I never had an issue.
You only had one what?
We only had one store where I lived.
Oh, you didn't live here. Okay.
Yeah.
My family never
Okay.
had that issue.
As inflation goes up, the amount of things like you buy goes down.
Yes, unfortunately, that is true. Stupid inflation.
I agree.
I have another one for airplanes. As the higher your angle of attack is, the lower speed you
Okay, cool. He's talking about when you're flying in a plane.
That's cool.
Because I don't know if you know this, but Jorge's going to be a pilot. He might get his license this summer, in fact.
That's cool.
get.
But down the road, you might get onto a jet plane, and he'll be like, "This is your captain speaking."
Hey, we had not do that.
Anyway, angle of attack is that angle. Obviously, if you're steeper, you can't go as fast, right? Right? Okay. Good job, Jorge.
I have one for
The faster
when
you
you're
go in the
so
car,
That would be going up, right? Down would be the
Yeah,
opposite.
what if it's steeper
Then
the
you're
other direction?
going down, you go faster and faster.
This right. Okay.
Sorry.
So when you fill up your gas tank, the amount of space you have left to fill up goes down while the price goes up
That's
by a
true.
lot.
Oh yeah. And we're heading into summer when it's more expensive too. So. All right, so here's an example of K. So if we take X, Y, what is the constant product throughout here?
2, 3.
So are you thinking this way? X, Y equals K. Any other numbers to throw out?
5.
So what is K? Does everybody see X, Y? X times Y is always 12, right?
Yep.
Okay. So it's not, we do need to be a little bit careful with this concept because I can't just randomly choose numbers, one going up and one going down. In this case, it's always, whatever we pick for numbers has to equal 12. That makes it inversely, inverse variation. So some of these things we were talking about, they have the concept of one going up, the other going down. As long as they were proportional to some constant like this, then it would be okay, right? Which a lot of these would have been. So what would be another number that I could put in here? Or maybe another couple. That would be,
24 and 25.
okay? 0.33333.
Yeah.
Okay, all right, you get the idea. So it always has to equal 12. As one thing's going up, the other's going down proportionally, okay? Maybe, did I make that clear? You know what, probably not enough. So let's put that here just to make sure that we are clear. So just add in a proportional manner. And then K is that constant that it always multiplies to B. Okay. Do you see this idea of when we were talking on the blue slide, as x goes to infinity, that thing came down to 0, and as x went to 0, y became infinity. Do you see that inverse relationship now? Okay. So that is our parent function for this type. I'm going to box this, probably 2 boxes. I'm going to put a big highlighter around it because this is our new parent function. And it's called the reciprocal function. And I guess I'll write the word parent. The F kind of got lost in that line. Oh, now I lost the L. Reciproca? That would be a good name for a math teacher's daughter.
Yeah.
Yeah, I don't know.
I would feel bad anyone named
Alright, so 1 over x. 1 over x is our new parent function. Okay, we'll put in a couple details about it. Go ahead and sketch that graph that we had on the blue slide.
You still have to like put your x and y axes for us.
Like how?
Well, that's just good form.
I know you guys don't know where they are.
Lexi.
Yes.
Yes, says Blaine.
It just depends on how they're how are they doing?
Alright, what does that little plus sign mean on the 0?
It's coming from the right.
Yep, so as we approach 0 from the right, this is shooting up to infinity. Okay? And then the limit as x approaches 0. How do we do the left, you suppose?
Negative.
From the left is what? Will I be able to put that on there?
-0.
I'm gonna write that better. It's not negative 0. It's from the left.
Okay.
Equals negative infinity. So it's shooting down. Okay? What?
There's a negative.
Yeah, okay. Maybe let's describe this for this first time. To 0 from right.
Rewards, 997 more.
To 0 from left. Alright, we have one more to write. We can combine this one. I'm okay with doing that. The limit as x approaches positive or negative infinity is what?
0, positive, negative.
Just 0. So in other words, as it goes further and further to the right, our y values will get closer and closer to 0. Yes, on the right it goes from the top, on the left it comes from the bottom. We'll just leave it at this for now. Guys, I did notice on this test that some of you are confused on the limit ideas. And you're like, it's either confusion or you're being lazy and don't want to write them out. Just write them, okay? It's important to do that. All right. What can x not be?
0.
Why?
Because you can't do 5 by 0.
Okay, so we'll start establishing this idea now, but
That's a big explanation.
yeah. I'm gonna do another one just for you.
How do you say it?
The denominator cannot be 0. In this case, it's x, but if it's x squared minus 5, then x cannot be the square root of 5. Okay? Whatever makes the denominator 0 is a no-no.
So x could be 0, it could just be -1.
In that case, if it was x squared minus 5, then yeah, x could be 0, 1, 2, 3, 4, anything up to square root of 5, right? Alright. What is the domain of this guy?
Negative infinity to, wait, to,
Negative infinity
well,
is
because it
zero,
can't be 0.
zero.
It can't be 0 because it never hits 0.
Your touch was
So
right.
the number would be infinity again, or something.
It's everything but 0, isn't it?
Yeah.
How about the range?
Everything but 0.
Also the same, everything but 0. So
How would you write that?
you're welcome to use interval notation. I don't know if you heard Tom. I'll show you this first one, but you can write it as union, do your whole intervals like this. That's okay. And sometimes students connect better with that. We can also write this in a shorter way, which is this. A brace, say all values of x, line, x cannot be 0. Brace. That says the same thing without doing all the intervals. Because some of these, you're going to have to break this up into like 3 or 4 intervals. And it's easier just to make a list of things it can't be instead of doing 3 or 4 intervals. Okay, same with the range. Only this time we need to use y. So all y values except 0. That's how you read that. All y, all x's are good except x can't be 0. There's a clock on the wall. So I would personally start adopting that notation, but you're, again, welcome. I will not grade you differently if you do intervals. Just make sure you do them correctly.
Oh, shoot.
So, new parent. Good?
Yeah.
Line.
You just offended the reciprocal function. Alright, is this inverse variation? Don't shout it out, just let me know with your thumb. Yes or no. Is this inverse variation?
Wait, 1. I can't tell. It's a little hard to read because of all the fractions.
Wait, I actually
Oh, wait, yes.
I like how you
Times
specifically.
Oh, yeah, no, that's so. No big deal.
Oh, you're voting. Yes or no? Oh man. Fractions are the bane of people's existence.
No, X's.
What is half of 15?
30.
7.5.
Oh, I'm.
What is half 1 times 7.5?
So,
What's 3 times 2.5?
7.5.
Wait.
What's 5 times 1.5?
7.5.
how's it, wait?
What's the
5?
3 times
times-
6. 3, what?
Wait, what?
3
Three
times
times
2 is 6,
two
and
is-
then 3 times 1/2 is 1.5.
Oh, are you
Well, I was like,
kidding?
hold on.
So is it?
So I have a.
What is K?
Okay, so I know that one.
Hooray.
Remember inverse variation, reciprocal function, x times y has to equal the same thing. So a constant. Good?
Yeah.
Okay. There was one up here. See if you think that one is inverse variation.
Well, you. That's 5 times 5.9.
Give me some math pieces. Okay. 3 times.
I couldn't see your thumb was behind him. Alright, are we saying yes or no?
No.
Okay, this one is 19.8, and this one is definitely not 19.8, right?
27.5.
Do we need to keep checking?
No.
No, because it's not the same proportion. It's not xy equals a constant. Even though, like this one is going down and this one is going up, that's not sufficient, right? It has to be always the same.
Some.
Although, if you did want to keep going, the next one is 30.8.
Okay. I don't want to do this too much. I guess you could potentially have an SAT question on this. Why don't you give that one a shot? It's probably like a 30-second job. So we start off with this, x times y equals k.
Oh.
And then we're told 10 times 3 equals, we don't know k, but now we know k is 30. Okay, so our function rule is y equals 30 divided by x. That's the, if we isolate y like we typically do, or f of x, then this would be our function rule. Okay? So now you're looking at a reciprocal function, aren't you? As we get closer to 0, 30 divided by something tiny is what? Something gigantic. 30 divided by tiny is gigantic. Think of it this way. If this is 30 pizzas, and I'm dividing by crumbs, right? 30 pizzas divided by how many crumbs are in a pizza. Is that a big or small number?
Gigantic.
That's a gigantic number. That's the idea of getting closer to 0 and having this thing shoot up.
That'd be like in the
Okay. Versus as we go out to the right, 30 pizzas, and now we're dividing by 10 million people. How much pizza do you get if I divide these pizzas by 10 million people? Hardly, like a molecule, right?
Yeah.
Right? Okay.
Rose on the cut.
You will leave hungry. So this is our reciprocal function, inverse variation rule. Anyway, from here, then we say y equals 30 over negative 5. Sorry, negative 6.
Negative 5.
Okay.
What did you do? I got it.
Good?
Yep.
One second.
Those are the same.
I'm multiplying.
Oh, here's another one. Any guitar players in here?
6.
Or any stringed instrument player? You play guitar? Good job, that's awesome.
I have
Are you
it.
pretty good?
This is Dawson.
So you like to?
Yeah, I have a guitar.
Good job. I play some. I'm not very good.
I need to learn how to play. I've had this guitar in my room for like 7 years. I got it when
I'm good at
I was 10 when I got it, and I haven't been able to learn how to play it yet.
Yeah.
So,
Guys, so hold on one sec. On a guitar, have you ever seen an artist put something across the neck?
Yes.
It's called a capo.
Uh-huh.
And basically what it does is shift the key so that maybe if you want to sing a song higher than it's written, or higher than playing up here, if you slide this thing and clamp it down, then you can play the notes and the strings like normal, but it's a higher key. It's cool. It's called a capo. But if you've taken physics, you guys, if you've done sound physics yet, so the relationship between cycles per second is called hertz. That's what makes the pitch of sound that we hear. So the higher the frequency, we measure it in hertz. It's called frequency. The higher this number, the higher the pitch is, and the lower then vice versa. Okay. But longer strings vibrate slower than shorter strings. So what do you expect the pitch to do as you shorten that down? It should go higher, right? Because the shorter the strings, vibrating faster vibrations is a higher pitch. And that's not just for guitars. This is sound in general. Okay. Have you learned the Doppler effect?
Nope.
Okay.
Never even.
Have you ever been standing on the side of a road or here just outside and the train goes by and it's like high pitched and then it gets lower? Like, have you ever heard that? Yeah. That's
My
called,
cousin makes those sounds.
that is called the Doppler effect. And it's this, okay? Sound is a compression wave. It's called longitudinal. Anyway, as that car is coming toward you, this is you. The waves are stacked up against each other as they're getting closer to you. So it's high pitched. And then as it goes past you, they get farther and farther away. Farther apart, rather. So it's a lower sound. Same idea. Only it's not a vibration, it's sound compression as it gets closer. So you've all experienced all this. All that to say, go ahead and give me the frequency when the string is 13 inches, please. Okay?
Because I thought
Actually, a little bit.
Oh, it's hidden?
I was like,
Guys, we have a 26-inch string, and we have our cycles per second, our frequency, as, actually before I do that, let's write our rule, x, y equals k. So we have 26 times 329.63 equals k. So we need k.
8570.12.
Okay, now when we shorten the string, we can figure out what our sound will be. So y equals this 8570.12 over our string length. Okay, so we just need 13 substituted in there.
Oopsie, I made this like
So
this
it's
calculation.
659.5.
that divided here.
Point what?
424.
Every time, like, we were watching this, right?
By like 6 times.
Which is double, right? Double 329.63.
So I was
So what would the pitch be? Higher or lower? Higher, because our frequency is higher. Those two are directly proportional. All right. Did that. Tell me what you think things. I already mentioned this. Let's see if you picked up on it.
I just skimmed through and I placed.
What is going on right now? Nobody's listening.
Sorry.
I'm
We should do 7 cents.
What do you think this 10 does
And I placed
to our reciprocal function?
Um,
I said it earlier. Let's see if you picked up on it.
drives it away.
Okay. So it's like a stretch, right? If you think of it like this, 10 times 1 over x, that's like a. So it stretches it away. In this case, it's a little bit harder to visualize. Here's our parents, would go through there. And then this 10 would make this be 110, right? If I plug in 1 for x, 1 over 1 times 10. Anyway, it's not going to be on there, but it's going to look stretched away from the origin. It's a different version of stretch than what we saw before. So what would we do to make it get closer to the origin?
Smaller number.
Like what?
Like
Something
one.
smaller.
0.000000.
Something smaller.
Well, it doesn't have to be that tiny. Like, what if we just call it 0.1? Now it's going to suck in closer to the origin more. Make sense?
Yeah.
Okay. How do we shift that thing?
By making.
Like, here's an example. What would this graph look like? I'm going to leave 1 in the numerator. X minus 5. What would that do? Right 5? Okay. So the way I want you to think of this is our new origin. So now our graph is there. Okay? It's an origin shift.
Yes.
What about if we added a 3 here?
Then it'll
It'll
go.
go up, over, right, left, 3. Wait, right, 3.
Okay, our new origin would be here, but same shape. What if I stick a 10 on top now?
Then it'll go farther away from the graph.
It'll be stretched.
Okay, now it's going to come further away, like stretched out, but relative to our new origin. Okay. Any questions on that stuff?
No.
Yeah.
If the numerator is equal to the denominator, wouldn't it just be a straight line?
Yeah. But it won't be if we have an x down here, because that creates variation, right? If this x wasn't here and we happen to have like 10 over 10, then yes, it would just be a horizontal line.